Okay, this video is a little bit less about second derivative, but it's an interesting exercise, I think. You may want to actually draw this in your book. So, well, you could do that for the other videos too, considering that I'm not in a classroom doing this on a whiteboard. Now, what I've got here is the derivative of a function. Right? This is the derivative, this is the gradient function. Okay. And the exercise is, could we get back to the function? So most of what we've done is say, here's a function, let's now think about its derivative, and then if we take the derivative of the derivative, we could get to the second derivative and so on, right? With this particular function, it's already a derivative, and we want to think, how could we sketch in the original function? Right? This is a cubic starting low, ending high. The original function must be a quartic. Okay. And this function starts with a negative gradient. So on the function, given that this green line is our gradient, right, here we have negative gradient values. So this function must be going downhill. It's probably starting up here somewhere, and it's coming down hill, right, until it gets to this point. At that point, the gradient equals 0, and the gradient has gone from negative to positive. If you imagine this on a sine diagram, you put in your, where does f prime x equals 0 on this sine diagram, and then you write negative, positive, and you say, well, this point there has to be a minimum. So it'd be coming down, and then we'd have a minimum, right? Okay, up here, the gradient is positive, right? And the gradient value increases up until this point, right? At this point, the gradient reaches its maximum value, and then it starts to decrease. Right? Now, it looks like a maximum on the gradient function. It's going to look like a point of inflection on the original function, right? So we've got a gradient that's increasing in its value, and then it starts to decrease, right? When a gradient's increasing, well, that's when you have concave up shape, right? So like the U shape, gradients are increasing. So we've come from our minimum, we've got our concave up shape, but somewhere around, not exactly sure how high, but somewhere we're going to have a point of inflection, well, at exactly x equals 2.125, we're going to have a point of inflection, right? And we're going to change to concave down shape at that point, okay? Now over here, right, we've got a gradient that equals 0, and we're going from positive values to positive values, right? Imagine your sine diagram again. So you're going to have x equals 4 on the sine diagram, right? First derivative equals 0, where x equals 4, and you're going to have plus, and what's that going to be? It's going to be another point of inflection, right? Here is the function, original function. So where gradient values were negative, we were going downhill on the function. When we got to gradient equals 0, we had a minimum on the function. Where we got to this local max on the gradient, right, we have a point of inflection. It's a non-stationary point, as you can see, because it doesn't equal 0, right? So the gradient is not 0 there. But here, gradient values are increasing. Here they start to decrease, and we've gone from this concave up shape to concave down shape until we get to here, x equals 4. We now have a gradient equals 0, and we have a stationary point of inflection. So I think that's quite an interesting little problem to pose yourself. So can you go from functions and can you look at a function and then imagine what a graph of its derivative would look like? But can you also look at a graph of the derivative and then imagine what the function itself would look like?